All right, here it is, last topic for the unit, and it's about hydrates. Hydrates. I wonder what's involved in a hydrate. Maybe when you stay hydrated, you're drinking water. So maybe water's involved? Yes. So hydrate is a compound with a specific amount of water molecules bound to it. So there's certain elements that you could use that if you can have water, or it could be without water. So these things are called hydrates. What's the overall purpose and how can you use these things in real life? Well, hydrates are often used as drying agents or desiccators. Desiccators are something that can absorb moisture because they absorb moisture. So like this, if you've ever seen these little silica gels that you in like electronics or shoes or nice clothing, or like my daughter loves eating little seaweed packets, and so this is one of the things that's down there to keep it dry because it's absorbing moisture. So silica gel, do not eat it because it's going to absorb your moisture. And then like kitty litter, same kind of thing. So silica gel used in electronic equipment, packaging, cat litter, seaweed, all that good stuff. These are hydrates that have been dehydrated. So in essence, they're absorbing moisture from the environment. So what are we doing? Well, we have hydrates. In order to name the hydrate, use the name and the formula need to show the number of water molecules. So the name uses the word hydrate with a prefix. So in essence, I have calcium chloride dihydrate. So this is kind of going back to our last unit where we talked about naming different compounds. And so notice that there are going to be ionic compounds where you have calcium chloride dihydrate. So dihydrate is telling you that there's two waters. Chromium 3 nitrate hexahydrate means that there's 6 waters. And so if we're going through, you'd have your ionic compound that you name and then your amount of waters. Dependent upon the amount of water will determine the prefix that goes in front of the word hydrates. So that's just kind of some background information. I'll ask you to practice a little bit how to name hydrates. And so why are we talking about hydrates when we've been talking about empirical mass, formula, the molecular formula, and so on and so forth? Well, it's a great question, because chemicals that do not contain water in their structures are called anhydrous. Sorry, this is just a little tidbit here. Anhydrous without water, but then hydrates can be anhydrous without water, but then they can absorb moisture and turn into something totally different. So you could have anhydrous cobalt 2 chloride, looks like this. There, if you add water to it, it becomes cobalt 2 chloride hexahydrate, and so that would turn the compound and make it look totally different like this. So in kind of looking at this, why are we talking about this with what we've been discussing this unit? Well, because it's going to be important for us to be able to determine the formula of a hydrate. And so once again, that we've done previously, first step is determine the number of moles of water and of anhydrous compound. So how are you going to do this? Well, you find the moles of water, divide by the moles of anhydrous compound, plug in X, the formula will be X times the amount of waters. And so we'll do an example of what that means. So what is the mole ratio, or what is the formula for the hydrate CuSO4, and what is this number? So we're looking at how do we name this hydrate. If the anhydrous mass of copper sulfate is 25.42, so in other words, without water, and there's a mass of water of 14.3 when it absorbs moisture. So if I have the copper sulfate without water weighs that much, and then with water weighs 14.3 grams more, because that's how much water it can absorb. Well, let's take a look. We need to figure out what is the ratio of this amount of copper sulfate to this amount of water. And so that kind of leads us back to what we've done before. Copper sulfate is CuSO4, and then our water is H2O. And so we have the mass of both. We have 25.42 grams, and we have 14.3 grams. And so we can't really look at the ratio of those using the masses. We'd have to look at it using the molar masses. And so using the molar masses, we can determine that the molar mass of H2O is 1.01 times 2 plus 16.00 grams per mole. So that ends up being 18.02 grams per mole. I'm going to put that on the bottom here for every 1 mole. And then copper sulfate, if you were to go through the math and figure out what is the mass of copper sulfate, you could figure out that the overall mass of CuSO4 is going to be 159.61 grams for every 1 mole. Let me make sure I'm good there. So 4 times 16 plus 3. Yeah, I'm going to go with 159.262. So that's the molar mass overall of the copper sulfate. When you do that, you end up getting this calculation. So grams get canceled out, 25.42 divided by 159.62. The moles of copper sulfate is 0.1593. I'm going to use 4 significant figures because there's 4 there. And then when I do 14.3 divided by 18.02 for the water, you end up getting 0.793 or 794 moles. And so that's not a very good ratio, so that you need to divide by the smallest number of each, which is the amount of anhydrous hydrate. So when that happens, you get, for every 1 of these copper sulfates, you will end up getting, let's see, 0.794 divided by 0.1593, 4.98, which we're going to say is 5. So in essence, we have 5 of these waters. So our formula would be CuSO4 dot 5H2O. In other words, this would be copper 2 sulfate, and then this would be what? What is 5? Pentahydrate. Great. So in essence, very similar to what we've been doing before. Now we're just kind of taking a look at the masses that are present of an anhydrous hydrate and the amount of water there. Depending on the mass, divide by the molar mass to get the moles of each. Look at the moles of each to get a ratio. It's a 1 to 5. It's always going to be a 1 to something ratio. So hopefully that was helpful.